Hi class, I'm going to discuss chapter 1 today with you, and this is going to revolve around the properties of matter. Now, the one thing that I want to discuss with you is basically what does chemistry mean to you? I know several of you might be thinking that chemistry is all about white lab coats, colorful solutions in Erlenmeyer flasks, but really, if you think about it, chemistry is anything and everything around you. The study of composition of materials around you, the properties of those materials, and how maybe one material gets transformed into another form. All of those are studied. They do fall under the broad science called chemistry. So when somebody says that they are studying chemistry, they could refer to the composition, the properties, transformation, the processes involving material particles. So the next question is, what is matter? Well, anything that has both mass as well as volume, no matter how minuscule the size might be, you would consider that you would call it matter. Now, when we make certain observations, when we are carrying out a study, let's start with a study. When we are carrying out a study, there are several stages that one would come across. The first one is called as hypothesis, and hypothesis is considered as a tentative interpretation. It's a very temporary tentative interpretation of results for a pertaining experiment that you are carrying out. The next stage is theory, which essentially would be an explanation of various observations made by various different people all across the world over a given period of time. And a theory can become a law when you are able to explain what we know about that concept. In addition, you're also able to predict certain things about future. So in addition to what you already know, you would be able to make certain future predictions as well. And only then, when you make these studies over a significant long period of time, let's say 100 years or so, a century or so, that's when you would call it a law. So as expected, law is something that is set in stone. Newton's law of gravitation, the apple always falls towards the earth because of gravity, and it never flies away. So whether it's an apple or it's a ball, if left, if no force is actually holding that apple or ball or a book, it is going to fall towards the earth, and that is set in stone, like I said. Now, before you get into a concept, it's important to realize, I'll give you a scenario. Let's say you are stranded in the Gulf of Mexico somewhere, you're thirsty, you want water. There's no water to drink. You ran out of all of your water reserves, and you don't have any more water, and you're kind of on a boat, like a castaway type situation, and now you want water. There's a lot of water around you, but it's not worthy of drinking. What would you do? Well, one might say it's seawater. If by some means you were able to distill off and separate out the salt from the water part, then you might be able to actually generate water for yourself. And that is exactly true. But my question would be, how do you know that seawater is not drinkable? And someone might say, well, because it contains a lot of salt in it. My question would be, what does salt do to you? And the answer to that is, as some of you might even know, essentially salt is going to cause dehydration in our body, and it could be so bad that it could be even fatal. Now, realize a couple things here. I'm hypothesizing that seawater is not worthy of drinking. This is a tentative interpretation. There's a lot of water, I can't use it because that water is undrinkable. So this is like a tentative interpretation, but I need proof. How can I prove it? Well, you can simply boil the water off, and if salt remains, then you know that salt was present in it in the first place. This action that you run is what is called as experimentation. So before you can prove your hypothesis, you really need certain experiments for that concept. And once you have proof from those experiments, you can then say that that hypothesis can be given a new status, and that status will be called as theory. So let's say I run an experiment, I find salt, you run an experiment, you find salt in seawater, 3 other people do that, and we continue to do this over a period of maybe 5 decades, and everybody seems to be getting salt when they evaporate off water from seawater. What does that tell you? That tells you that seawater is undrinkable. It cannot be used because it contains a ton of salt in there. So we had to run an experiment to prove our tentative hypothesis, and that is when it got transformed into what is called as theory. Now, the next observation that we made, or the next tentative hypothesis was, well, seawater causes dehydration. Is there a proof for that? So again, certain experiments will need to be done if actually human cells lose water and go through a dehydration process when they're placed in seawater. And if that is true, then you can claim that that particular observation is true as well. So please realize here that you really need to carry out experimentation to bring the status of a hypothesis to the theory level and the status of a theory to become a law. And once something gets the status of a law, that scientific method is already now established, that is now set in stone. If that is clear, let's move forward and learn about one of the laws. And the laws I have here is the law of mass conservation, according to which mass can neither be created nor can it be destroyed. So it's very similar to law of conservation of energy, where energy cannot be created or destroyed, and it can only be transformed from one form to another, something we'll learn in chapter 6 when we learn about heat energy. But let's now focus on the law of conservation of mass. And as you can see here, I'm showing you the example that mercury and oxygen, which are present as the elements together, they have gone through the reaction and HGO was born. And so when the reaction occurs, the amount of mercury oxide that will be generated in the reaction is going to be no more than the total amount of mercury and oxygen that was taken in the first place, provided that we have not allowed any loss of mass. That means no gases were allowed to escape, and that is when you would say that law of mass conservation is going to hold true. As an example, let's consider another case. This is formation of carbon dioxide from elemental carbon and oxygen. And I have here that 12.3 grams of carbon reacts with 32.8 grams of oxygen to give you how many grams of CO2? Please realize, if law of conservation of mass, if that holds true, then the left hand side of the mass, that means the mass of the reactants, should be same as the mass of product. What that means is 12.3 grams of carbon plus 32.8 grams of oxygen together. All you have to do is add the two numbers here. So 12.3 plus 32.8 on my calculator is showing me 45.1. So 45.1 grams of CO2 will be generated. Likewise, if you know a certain mass of CO2 and you know a certain mass of carbon, you would be able to determine the mass of CO2 that is associated, that will be required for this reaction to go to completion. So hopefully you can work on the other two bits, B and C. Let's consider law of definite proportion. Now, law of definite proportion states that if you take different samples of a pure substance, it always will contain the same proportion of element by mass. What does that mean? That means that if you consider water, let's say water from the sparkling water or the spring water, or as long as it's H2O, it is going to contain 2 hydrogen atoms and 1 oxygen atom. So as long as we are referring to H2O, it is going to contain 2 grams of hydrogen with 16 grams of oxygen, and together they would form 18 grams of water, and this is going to remain consistent again as long as we have H2O in the system. Ooh, what happened here? Let's take it forward. Okay. All right. So what I'm going to spend time in the next couple minutes is the 3 physical states of matter, which you probably already have studied in school. So hopefully it's going to go pretty fast. There are 3 different phases. We have solid, liquid, and gases. And hopefully you realize from school perhaps, or a previous chemistry class, that solids are the one in which molecules are really close to each other. Liquids are the one in which they are slightly far apart, and gases are the one in which they are really far apart. And I think I have a picture to show that. Why doesn't it? To show that to you. Let's go, let's scroll down. Yeah. So here you can see solids, the molecules are jam-packed, real close to each other. Ice is a great example. In case of liquids, you are able to see the molecules far apart tad bit, and in case of gases, each molecule is discrete and it's far away from each other. That's the example is steam. So if you think about it, solids will have a definite shape, they will have a definite fixed volume, and you can't really compress if solids. If you try to apply pressure on that, it probably will break before it can go through a compression process. Liquids, on the other hand, they take the shape of the container. So for example, if you take milk, that looks like it has the shape of a milk gallon, the shape of that container, and when you put it in a tumbler, it takes the shape of the tumbler, and so they have a variable shape, but the volume is still fixed. Of course, again, the compressibility is negligible. Gases, on the other hand, will take the shape of the container. They do not have a fixed volume that is variable, because every inch of the given container can be taken up by gas molecules because they have so much energy in them, and compressibility is significant because you can bring the gas molecules really close to each other. So if I have this sample, I can apply pressure from all directions, and so these molecules will come close to each other, and eventually it might just liquefy. So realize that the 3 phases are different, and the properties are different, but hopefully you can see that as you increase the energy, you can bring a solid to a liquid and a liquid to a gas. Gases will have the highest energy and solids will have the lowest energy, and like I said, as you increase the temperature, you're going to move from solid to liquid and liquid to gas. I'm going to continue the discussion in the next video.